In today's lecture, we will be looking at substitution reaction. Actually, this is the first lecture of two for substitution reactions. So in this presentation, we will do a quick review of substitution reactions. Next, we'll get into a little more details of substitution reactions and look at one mechanism in particular, and that's the SN1 mechanism. We'll cover that in more details. So we'll look at we'll examine the substrate or the electrophile. Then we'll look at one of the intermediates that's formed, the most important intermediate, the carbocation intermediate. Then we'll look at the stereochemistry of the products and the nucleophile of the reaction. We'll discover it is also the solvent for the SN1 reactions. Next, we'll look at some examples using SN1 reactions, the application of SN1 mechanisms to substitution reactions, and lastly, we'll do a summary of SN1 reactions. Okay, so let's begin. A substitution reaction is shown below. So it involves literally a nucleophile reacting with an electrophile in which there is a leaving group on the electrophile. So that concept is illustrated below. Here is a nucleophile, and as you remember, a nucleophile is a Lewis base. It has an unshared pair of electrons. It could be charged or it could be neutral. We'll discover in today's lecture that for the SN1 it's typically neutral because it's the solvent, but most important, it must have at least one unshared pair of electrons. The other reactant is the electrophile, and as you can see here, it has L, which is defined as a leaving group. So when the reaction is done, L leaves with its electrons, shown here as a leaving group, and the nucleophile is now bonded to the carbon to form the organic product where a new bond is formed here. So here's some reactions. Give an example. So we have here the electrophile and here the nucleophile. So this reaction is classified as a nucleophilic substitution at an aliphatic carbon because this carbon here is sp3. We'll see other substitution reactions later on. But this is the solvent here. This is our leaving group. Here it is. And here is our nucleophile bonded right here. Another example, nucleophile here, electrophile, leaving group. Here's our leaving group, Br minus. But of course, since there is a counter ion, it's a salt, and this is the new bond right here, and this is our organic product. Same here, leaving group. Let's put the leaving group with the electrons because it comes off as Cl minus, and our nucleophile has an unshared pair of electrons, which forms that new bond. So that's examples of nucleophilic substitution reactions. One particular mechanism, however, to explain these reactions is the SN1 mechanism. Substitution nucleophilic unimolecular. We'll see why it's unimolecular in a second. So here's the electrophile. It leaves in a step taking the electrons to form a leaving group right here and a carbocation, because these electrons are now bonded to the leaving group. So the first step involves the heterolytic breakage of this bond to give a carbocation. As you can imagine, that's a slow step requiring energy because a bond is broken. So this step is called the rate determining step. You will recall from previous lectures, the rate determining step determines the overall rate of a reaction. In the second step, so notice there are two steps to an SN1 reaction. The second step is fast, where the nucleophile, the electrons of the nucleophile, forms a bond to the positive carbocation, and here is that bond, and that's the substitution product. And as you can imagine, this step is fast because we have here a carbocation intermediate forming a neutral product, stable product. So this step here is a fast step. Here is the summary of the SN1 reaction. A electrophile has an heterolytic cleavage to form a carbocation in the rate determining step. In the fast step, the nucleophile reacts with a carbocation to form the substitution product. You'll see another term for this reaction here, or this mechanism, is unimolecular substitution, SN1. Why? Because there's only one molecule in the most important step of this reaction, the rate determining step, and that's why it's called unimolecular substitution, or SN1. Here's a graphical illustration or energy profile diagram to describe the concept that we just for the SN1 reaction. So the first step is the formation of the carbocation here from the reactant. So here's the reactant going through a transition state, bond breakage, onto the carbocation. In the fast step, the carbocation reacts with the nucleophile to give the substitution product. Notice that this activation energy here is pretty high compared to this one. So that is why this step is the slow step. And you will recall from Gen Chem that the larger the activation barrier, the slower is the reaction. So this is really the RDS right here, and this step here is the fast step. That's why the activation barrier here is much smaller. So in terms of why this type reaction occurs, typically we have a leaving group that's electronegative. So this is a polar covalent bond where the electrons here are closer to the electronegative leaving group compared to the carbon. So this is partially negative and this is partially positive. So that's the driving force for this. So there's a heterolytic cleavage, because we have two electrons here going on to the leaving group and forming a carbocation. I should point out here though that the leaving group here, if it's a good leaving group, it is also a very stable conjugate base. So good leaving groups are stable conjugate bases. Of course, you will recall from last lecture that a stable conjugate base or weak conjugate base comes from a strong acid. So that is why we have I- as a better leaving group than Cl minus, for example, because HI is a stronger acid, which means this is a weaker conjugate base compared to HCl, which is a weaker acid, and hence here a stronger conjugate base, poorer leaving group, even though it is still a good leaving group. So let us look at some examples here. So here is our electrophile. Here is my carbon. Here is my leaving group. All of this, so this bond breaks, putting the electrons on the oxygen and forming a carbocation in the process. These electrons can be delocalized. As you'll notice here, this is the carboxylate anion, or the acetate anion here. And it's resonance stabilized, which means it's fairly stable, which means that it is a good leaving group. Here's another good leaving group. Breakage of this bond here puts the electrons onto the oxygen and forming a carbocation based on a heterolytic cleavage. As you can imagine, these electrons here are stabilized based on this sulfur oxygen double bonds. So this tosyl group, or the tosylate group here, is a good leaving group, a weak conjugate base, so hence a good leaving group. It's possible to convert a very poor leaving group. So here we have a very poor leaving group here in the form of OH minus. As you will recall, the conjugate acid of OH minus is H2O. That's a very weak acid. So therefore this is a very poor leaving group. I'll just write it here. So if it left, we would get that, the hydroxide anion. We all know that's a very strong base, so it's a poor leaving group. But it can be converted to a better leaving group upon protonation. So protonation of the OH here gives this. Now we have H2O as a leaving group. As you can imagine, water is here a extremely good leaving group, because it is a stable conjugate base and creates in the process a carbocation. So we can go from an alcohol here to a carbocation in the presence of an acid. Same for the amine. As you can imagine, the amine here is a poor leaving group, because that would mean the amide anion. As we know, that's a very strong base based on last lecture. That's a very strong base, so poor leaving group, but in the presence of an acid, it creates the ammonium ion. Now this is a good leaving group because it's a neutral amine, and of course the carbocation. So this gives you a strategy how to convert a poor leaving group into a good leaving group so that it can undergo a substitution reaction. So in general here we just have a summary. Again, we have here a bromide, fairly good leaving group, water, nucleophile, substitution reaction, OH, leaving group Br minus. Of course it picks up a proton from the solvent. So what we have here is the nucleophile here, which is also the solvent. So this type reaction is called solvolysis. So we have a couple names for this type mechanism: SN1 mechanism, unimolecular mechanism, and now solvolysis for the same type mechanism. So it works by, we have a heterolytic cleavage as expected here to give the carbocation and a good leaving group. Water now attacks, the nucleophile attacks. It carries with it an extra proton. So as you can imagine here, the Br minus takes this off to get HBr as the other product. But here is the organic product for that reaction that's undergone, so to speak, an solvolysis mechanism, or SN1. Let us look at the carbocation intermediate. We've covered this before because this is a intermediate that we've seen before, the carbocation. So briefly, it's an sp2 carbon where we have here a p orbital that's empty. So in terms of stability, you'd expect a methyl carbocation to be more stable. A methyl carbocation, which is right here, to be less stable than a primary carbocation, because here we have a carbon which has a hydrogen, and another carbon that has an alkyl group adjacent, so these electrons can help stabilize that vacant p orbital. So we would expect here a primary carbocation to be more stable than your methyl carbocation. You know what's coming. Here we have a secondary carbocation, because we have here a carbon that's bonded to two other alkyl groups. They can provide stability to the carbocation, so hence the secondary is more stable than the primary. As you can imagine, the tertiary carbocation has 1, 2, and 3 alkyl groups that can help stabilize this, so the tertiary carbocation is more stable than the secondary and more stable than the primary, and of course a lot more stable than the methyl. We can also stabilize a carbocation, as we have seen in the previous lecture, by resonance. So this is the benzylic carbocation, which is adjacent to the benzene ring or the phenyl ring. These electrons here can stabilize that carbocation by delocalizing the charge from this carbon now to this carbon. It can go further to this carbon. So there's a delocalization of that positive charge of the carbocation, providing stability to that carbocation by resonance. Here's another form. If there is a substituent adjacent to the carbocation that has at least one unchaired pair of electrons, these electrons can stabilize that carbocation by delocalizing the charge from the carbocation to the adjacent atom, in this case the oxygen. So there are quite a few ways, as we've seen, in terms of stabilizing the charge. These are just a few. You will recall from previous lectures that we have homoconjugation, the non-classical cation, etc. So you may want to go back and review those forms of stability for the carbocation. So in summary, we have here the benzylic is more stable, and about the equal instability to the allylic. Of course, you will recall that the allylic is the carbon-carbon double bond, and here is our positive charge. So we have bonds here on that. So that's the allylic. So they're about the equal instability, but more stable than the tertiary, more stable than the secondary, more stable than the primary carbocation, and a lot more stable than the methyl. As a matter of fact, it's argued in some books and publications that the methyl cation is not formed because it's so unstable, because there's nothing adjacent to stabilize that methyl carbocation. Let's look at the substrate in a little more details here. And this one is at a bridgehead carbon. So here's a bicyclic compound. Okay, so we have 2 rings, a 6-membered ring and a 5-membered ring. And here's the bridgehead carbon. So if this leaves, we have a carbocation here. If this leaves, we have a carbocation here. But notice the rate of solvolysis reacting with a solvent such as water. This is extremely slow, 10 to the minus 15, and this is extremely slow but a little faster, 10 to the minus 7. Can we explain that? One explanation is that this is the RDS right here, the formation of the carbocation. This carbocation is not stable because this bridge here will not assist in the formation of a sp2 carbon because it's tied up in a particular geometry based on this very tight arrangement of the bicyclic system here, where this is a 5-membered ring and a 6-membered ring. Expanding the bridge, however, from a 1-carbon bridge to a 2-carbon bridge gives a little more flexibility to this carbocation. So therefore this can assume a little better, notice a little better, the geometry of an sp2 compared to that here. So that explains why this reaction is a little faster, because this carbocation is a little more stable compared to this carbocation due to the strain of that bridgehead carbon. Let's look at another aspect here, the stereochemistry of the carbocation. So if we start out here with a stereogenic or a chiral molecule here, which has a good leaving group, in the RDS it forms a carbocation. It's sp2 with a vacant p orbital. This nucleophile, or the solvent in this case, since it's SN1, can attack from either side, and the probability here is 50-50. So we have an equal mixture of one enantiomer and the other enantiomer. Of course, as you know from general organic, that's called a racemic mixture. A racemic mixture consists of a 50-50 mixture of enantiomers, the R and the S enantiomer. Here are just some more examples. We have this bromide here. This is written a little differently here because we have the dashed wedge. Bear in mind that in the back here we have the hydrogen. So this is now the solvent, which is methanol. So we have the substitution product here, and this is racemic. Written differently, this is the Fischer projection. We have again the racemic SN1 products. Let's conclude by looking at the next few slides. We'll look at the effect of the solvent. So let's just summarize so far what we know of the solvent. So the solvent is typically, I should not even say typically, but it is the nucleophile for SN1 reactions. So it's typically the nucleophile for SN1 reactions. I should clarify, when I say typically, I mean here if you should include a salt such as which is a good nucleophile, you will get a mixture of nucleophiles, possible nucleophiles. Another point here is that since the solvent serves as the nucleophile, the reaction also is known as solvolysis. So again, these terms are interchangeable: solvolysis, SN1, or unimolecular. To assist in the generation of the carbocation in the rate determining step, the solvent is typically a good ionizing solvent. What do we mean by ionizing? That means that the dielectric constant, or the dipole moment, of that solvent is pretty large. Typically they are protic solvents that adds to the polarity. So in other words, if you have a solvent such as water it's considered a protic solvent because this hydrogen here is partially positive, and of course, as you can expect, that oxygen is partially negative and this is partially positive. Since this is partially positive, we say that's protic. So that hydrogen is acting as a proton and hence a protic solvent. So the same description can be used for the alcohols, or OH, where this hydrogen here is protic, so it's described as a protic polar solvent. As you can imagine, which solvent is the best solvent is a good question, and there are different scales, and there's one in the textbook that's the Weinstein Y scale that gives an idea of the solvent polarity and solvent ionizing potential of different solvents. So if you have to pick a good ionizing solvent for an SN1 reaction, you can look at this table and determine which has a better Y parameter for this reaction. But in general, acetic acid is a good protic solvent, alcohol is a good protic solvent, and of course, as we have seen before, water is a good protic solvent for SN1 reactions. Let us look at now the aspect of the solvent in terms of the reactions and unexpected outcomes. So the nature of the solvent can dictate the outcome of SN1 reactions. Let's look at this one, for example. Here is the carbon. Here is the leaving group, Cl, reacting this with acetic acid. So we'd expect the acetate anion. So we just added some more acetate anion here. We'd expect that to be the nucleophile. So we would expect here substitution. Of course, this would be racemic and not just one stereoisomer, because it can come in from either side based on the formation of a carbocation. So that's expected, but here is the product that was actually isolated. So it appears as if the Cl moved over to here. As chemists and as analytical scientists, we need to explain this formation. One explanation for the unexpected product is that this leaves to form the carbocation, but it remains in close proximity to the carbocation. So here's the leaving group, which remains in close proximity to the carbocation. And why does that happen? Because we have solvent molecules around it to keep it as a tight ion pair. So when this leaves, the solvent molecule surrounds the anion and the carbocation to keep it as a tight ion pair. So now we can see this coming back in to form the reactant, or it can go here to form the product. So this results based on the tight ion pair that exists after the heterolytic breakage of that bond. So in terms of effects of the solvent, as you can imagine, now we have different types of solvated ions which can actually dictate the product. Here is a tight ion pair, as we have described, very close to each other. So as you can imagine, if that happens, what you would expect is a return of the leaving group into the carbocation from the same side to give the product. We'll see an example of that in a second. We have another type solvated ion That's called the solvent separated ion pair, where the solvent now gets in between the carbocation and the anion. So it's separated but slightly. So you can expect for a reaction of this type, this is a bit further, so the return here is not as efficient as if you had another nucleophile, such as the solvent, coming in to form the product. So you'd expect here not 100% racemic, but a bit more retention, since this is coming back in to form the product, but it's separated. Here's the free ions. So here we have the carbocation that's solvated, and we have the anion that's solvated. So in this case, you would expect complete racemization, where the nucleophile or the water or the solvent can come from this side or from this side to form a racemic product if the reactant here is in fact chiral. So these are the different type ion pairs that you will see after the formation of a carbocation. A tight ion pair, a solvent separated ion pair, and free ions that are of course solvated from the solvent. Let us apply that knowledge and see if we can solve a couple of problems here. So let's look at this one. Alcohols react with thionyl chloride. This is a routine reaction that's carried out in the organic chemistry lab, where we can convert here an alcohol into a chloride. So this is another reaction of converting an OH, which is a very poor leaving group, to a better leaving group, the chloride, using thionyl chloride, SOCl2. If this reaction is performed in dioxane, which is a fairly non-polar aprotic solvent, let's draw it so you can see it. As dioxane here, notice there is no hydrogen that's bonded to electronegative oxygen. They're all bonded here to carbons. So this is a fairly non-polar aprotic solvent. In that solvent, there is retention of configuration as shown in 8. Notice retention of configuration. This configuration here is the same, except the chloride comes in from the same side to retain configuration. On the other hand, if we should add an additional chloride in the form of pyridine hydrochloride as a salt, there is inversion of product. The product is inverted to give 9. The question is, how do we explain that? So let's look at possible explanation. So in the first step of the reaction, here we have a very good leaving group in the form of SO2 right here. That's a gas, so that's a very good leaving group, and it's neutral. So that's a very good leaving group, forming a carbocation or carbocationic like right here. So then, since this is a good leaving group, the carbocation may not necessarily form, or the instant it is formed, this chloride ion here with its electrons come in from the same side to give retention product. So that's a subtle difference here, is that because this is such a good leaving group in the form of SO2, when this chloride is leaving, it comes into this carbocation as it's being formed to form the product. Another way of looking at this is that if this leaves to form SO2, we form a carbocation, but it's such a tight ion pair here that the Cl comes in from the same side to give retention. So this would have to be a very tight ion pair. So now we can invoke the concept of a tight ion pair to explain the retention of configuration for the product. Let's look at adding a additional chloride ion in the form of Cl-. This came from pyridinium hydrochloride. So here's the additional chloride ion using the same concept as before in an excess. This would have to come in from the opposite side as this leaves as SO2, and before this comes back in, so we have here inversion. So this Cl here is really this Cl here. Or we could look at it as we did before. If this leaves as SO2 right here, and of course we have a tight ion pair here, additional chloride ions from the pyridinium hydrochloride salt comes in from the opposite side of this tight ion pair. Notice the opposite side because this side is blocked with the leaving group, so this comes in from the opposite side to give the inversion of the product. So that's how we can explain. Of course, as you have seen from my exams, the typical question is to explain different observation using the information that's presented here in lecture. Just to conclude here, we have seen these type reactions before where we have a bromide or good leaving group connected to a carbon here, solvolysis, here's a solvent, methanol. We expect this product because we expect substitution here, but we get an unexpected product where the OH is bonded to this carbon, and it appears as if this methyl group here migrates. So as you can expect here, a good question would be, how do we explain this unexpected product? To explain the expected product is fairly easy because we have a heterolytic cleavage of this bond to form the carbocation right here. Here's the leaving group in the RDS. By the way, whenever you write a mechanism at this stage, please include the rate determining step, because that's important for the overall rate of the reaction. The solvent attacks here, and of course we get the expected product. The unexpected product is a little more difficult to explain though, because the first step, RDS, gives the same carbocation. But because this is a secondary carbocation, it can rearrange to give a more stable tertiary carbocation by this group migrating over to here in the form of a 1,2 methide shift, Y12, 1,2 carbons here to give a 1,2 methide shift, a more stable carbocation. Then in the fast step, the nucleophile, the solvent, attacks this carbon to give the unexpected product. So we have seen these type rearrangements before when we look at carbocations. So these carbocations here are the same type carbocations that we looked at when we looked at different type intermediates or reactive intermediates for different type reactions. Lastly, a summary of SN1 mechanism for substitution reaction. The mechanism is a two-step reaction. Notice it's a two-step in which the most important step is the rate determining step, in which there's the formation of a carbocation from the electrophile. So it's a two-step mechanism, but a unimolecular, because only one molecule, the electrophile, is used to determine the overall rate in the rate determining step. Regarding the electrophile of the substrate, the allylic and benzylic about equal stability, but more stable than the tertiary, secondary, methyl, and primary. Stereochemistry, racemic if the reactant is optically active. Nucleophile, the solvent is typically the nucleophile. Leaving group, good leaving group, weak conjugate base that results. So you can determine a good leaving group by looking at the stability of that leaving group, which is dictated by how stable it is, which is reflected by the strength of that base. If it's a weak conjugate base, it's a good leaving group. If it's a strong conjugate base, it is a poor leaving group. Solvent is ionizing, high dielectric constant dipole moment, protic solvent that are typically used for solvolysis. And the type ion pairing, as we have seen, plays a very important role in the stereochemistry outcome of a reaction, or in general of the outcome of a reaction. So we have three types of ion pair: the tight ion pair, where the leaving group is very close to the carbocation, very tight, but the entire is solvated. Then we have the solvent separated, and lastly we have the free ions, which gives, of course, as we said earlier, the racemic mixture. I think that's the end of this lecture. So continue studying while I put shortly another lecture on substitution reactions. We have 2 lectures for substitution reactions. I'll get that done shortly so we can look at substitution reactions, and the next type reaction we'll look at, I think, is the elimination reaction, but you can start reading up on that. Okay, so continue to study hard. Okay, bye.